Okay, let's start. It's 4:10. Okay, welcome everybody to the dissertation talk of Somil Bansal. And it's a pleasure to introduce Somil. So Somil works at the interface of control theory, machine learning, robotics, and computer vision. He began his PhD working in problems really related to control only, so real-time reachability methods in path planning for large groups of vehicles was a project that he worked on early on. And he became interested in learning, and he had this kind of trial balloon project where he tried out a neural network-based controller where he flew it on a quadrotor, learning the interactions in quadrotor dynamics. Yeah, okay, good. So he worked on this neural network-based controller project, and at that point, got some cool results. But really, I think it was at that point that realized, where is learning really crucial in control systems? And one of the areas that it's really useful in is perception. So learning about the world around the system. And from then on, that's been, I would say, the primary focus of Somil's work. His thesis and what he's going to present today is really trying to understand methods and develop methods for combining known models of an autonomous system with unknown but learned representations of the environment around it. Somil is, he's working on a lot of research. He's also a great teacher. He won a UC Berkeley GSI award for his teaching. And this year he was awarded the Eli Jury Award for outstanding research in the systems area. And he is going to be a professor. He has just decided to, he just accepted one of his offers. He's going to be an assistant professor at USC starting in the fall of 2021.
Thank you, Claire. Thank you for such a great introduction. And hello, everybody, and thanks for coming to my dissertation talk. Today, I will talk about the work that we have been doing for the past 4 or 5 years now on designing safe and data-efficient learning algorithms for robotic systems. So at a high level, my research deals with autonomous systems like these. So here we have surgical robots, autonomous cars, autonomous drones, service robots. And at the first glance, all these systems might seem very different from each other, but they have something in common. These are all safety critical systems. So we need to design algorithms that can actively reason about the safety of these systems as they work alongside humans or other robotic systems. And in fact, control theorists and roboticists have been working for decades now on designing such algorithms for autonomous systems. And these algorithms really form the basis of our chemical plants and thermostats all the way to our assembly lines and highly safety critical systems that I'm sure you must have all experienced, like aircrafts. In fact, as Claire mentioned, I myself come from a background in control theory, and early on in my PhD, I have been working on designing such safety algorithms for robotic systems. But to do this safety analysis, we often need to have a very good understanding of the environment and the conditions in which the system must operate. And once those conditions are known, we make sure that the system remains safe in those conditions. Now, that is something that is just challenging for future autonomous systems. So for example, consider an autonomous car. It needs to drive around block lanes, construction sites, around humans in all sorts of weathers like rain or snow. And all these conditions cannot be known beforehand. So for future autonomous systems, first and foremost, we need algorithms that enable these systems to adapt quickly to their environment and obviously do so in a safe fashion. Now the whole premise of my talk obviously is that we are not quite there yet. And what I want to do in this story is to share some of the steps we have been taken towards this goal. But if you think about these driving scenarios, as humans, we are really good at them. We are very good at perceiving our environment and making quick decisions to adapt to that environment. And that's because even though we haven't driven in the exact same driving conditions before, we have driven in the similar conditions. And we can use this prior experience to drive in these new situations. So on the other hand, there do exist these learning-based methods which enable autonomous systems to make novel judgments about new environments or to make judgments about the novel environments based on the prior data. And the basic premise of these algorithms is that they somehow map the sensor input of the robot. So for example, this could be the image of the environment that this robot is seeing to the control commands to be applied on the robot. And the idea is that this mapping is learned through data. So for example, here is a fetch mobile robot, which is actually navigating in Google Cafeteria around humans, around moving obstacles without having any prior knowledge about the environment. And it's only using the onboard sensor to do so. So this is an algorithm developed by researchers at Google. So these are the kind of behaviors we can enable via machine learning. But the challenge with these learning algorithms is that they often ignore the underlying physical structure of the system, and as a result are very data hungry. So for example, to learn this behavior, this fetch robot requires 7 million samples, which is just very hard to collect on a real robotic system. Now, the other problem is that these learning algorithms fail unexpectedly. So this video is pretty much a cliche at this point in the Bay Area, but this is a video of Tesla Autopilot where the car is colliding into the construction going on in the shoulder because the machine learning algorithm fails to recognize that construction shoulder. So we don't want these kind of behaviors for our autonomous systems. So, and here we have these learning algorithms which are adaptive, but then data hungry and potentially lead to unsafe behaviors. Now, when I started my PhD, there were pretty much these two separate lines of work for autonomous systems. The one that uses machine learning for autonomy and the other one were based on the control theory. Now, over the course of my PhD, I have designed mathematical tools and algorithms that unify these two perspectives. And my hope in today's talk is to share some of those ideas with you and perhaps demonstrate that how this unification between learning and control can lead to adaptation in the new environment, but do so in a data efficient and safe fashion. Now, one of the places where learning is particularly useful for robotic system is for perception. That is to perceive and sense the environment around us and make sense out of it. So first I will talk about how we can combine learning and control. Sorry, I think, can you still see my slides?
We see your, I think, your folder.
We see your mountain.
Looks like Keynote crashed.
Yeah, probably Keynote crashed. So let me just open that again.
If you can make cars not crash, maybe you could make Keynote not crash.
one day, Nick. Yeah, sorry. So I was saying that first I will talk about how we can combine learning and control to make judgments in the new environment based only on the onboard sensors. And then I will talk about what happens when these learning-based systems fail, how we can make sure that the system remains safe despite those failures. Now, I motivated this talk for general autonomous systems, and pretty much all algorithms and tools that I will discuss today can be applied to general autonomous system. But for the purposes of this talk, I want to use autonomous navigation as a case study to understand the interaction between perception and control. Now here, the problem is that the robot starts at some initial position with some heading, and it wants to go to a given goal coordinates in an indoor environment. So these, for example, could be the coordinates of the room that we want the robot to go to. We also assume that the robot can sense its own position at all times, but it does not know anything about the obstacles in the environment. So it does not know any of these gray boxes over here, which represent obstacles in this particular case. All it has is a monocular RGB camera mounted on the robot, which gives it the images like this. So it can see, obviously, in front of it. And based on these images, we need to navigate the robot to its goal without colliding with the obstacles. Now, just like for any other autonomous systems, there are pretty much these two separate camps of approaches for navigation as well, learning-based approaches and control theoretic approaches. So for the next few minutes, let me actually share my experience with these two camps of approaches and discuss how that kind of motivated our own framework that unifies these two perspectives. Now, within learning itself, there are multiple different approaches people have taken for navigation. But one of the approaches that has gained a lot of traction recently in the robotics community is end-to-end learning. And the idea of end-to-end learning is that somehow the images that the robot sees are mapped to the control actions for the robot. Now, when we actually tried this algorithm, it did enable the robot to navigate in completely new buildings that it has never seen before. But one, we required a lot of data samples to do that. But second, when we executed this on a real robot, these are the kind of behaviors we see, these stop and go behaviors. Now, coming from a control theory background, when I saw these stop and go behaviors, I thought there's a lot that we know about these systems which can help us mitigating some of these issues, such as a dynamics and physics model of the system. And on the other hand, to be fair, there exists approaches to navigation which have been using these models for decades. And these approaches are mapping-based approaches, sometimes also called SLAM-based approaches, which pretty much are the state of the art in navigation, our navigation systems out there. And the idea of these approaches is that they first use the images of the environment to identify all the obstacles in the environment, which is also called the mapping phase. And then once we know all the obstacles, we use a dynamics model of the robot or a physics model of the robot to plan a trajectory around those obstacles. And as I said, these approaches work really, really well, except that when you implement that on a real robot, you face a lot of engineering challenges. So for example, on the left, I'm showing you the input RGB image of the robot. So this is the image that the robot sees. And on the right is our attempt at identifying the obstacles in that image. And these black regions over here in these images represent the part where we could not reliably detect the obstacles. And you can see this process of detecting the obstacle fails around thin chair legs or when there are dark or bright spots right next to each other. This kind of happens when, for example, sunlight is present in the scene. And to be fair, we can overcome some of these engineering challenges by tuning the parameters of the mapping-based approaches, but that is just very hard and often tend to be environment specific. On the other hand, when I looked at these failure cases, I thought to myself that there's a lot of semantic in these scenes that can be just used to overcome some of these issues. For example, it's a chair, and we know chairs have legs. So maybe we can use these semantics to overcome some of the issues with mapping-based approaches. So a natural question to then ask is how we can combine or unify the complementary advantages of learning-based approaches and control theoretic approaches. And obviously there's so many people asking a similar unification question, but for the purposes of this particular problem that we are interested in, we are actually taking inspiration from humans to unify the two. Now, as humans, we regularly enter new buildings and we can navigate in that building without mapping that building necessarily. On the other hand, we do not necessarily reason about every footstep in that building as suggested by end-to-end learning. There's a lot of evidence that humans actually navigate based on these sub-goals. So for example, this is, by the way, the cubicle in which I sit. Suppose I start in this cubicle and I see an image like this, and I want to go to a goal area somewhere here, outside the cubicle. Then based on this image, you will not necessarily try to identify all the shapes of these chairs or tables. You will say, well, to make progress towards the goal, I need to go somewhere there next. I need to get out of the cubicle. Once I'm out of the cubicle, I see a hallway and I say like, oh, I want to continue down the hallway. And once I'm near the goal, I can just go to the goal. Now, intuitively, what this sub-goal is doing over here is it is capturing all the information in the environment that is relevant for the navigation task at hand. And again, we can do so because we have prior experience navigating in indoor buildings. So that's really our key idea, which is use machine learning for challenging sensory input and for high-level planning. In other words, use machine learning for the environment-level reasoning of the system, and then use control theory and models for the system-level reasoning. What that means in this specific context is that use machine learning for processing the image that the robot sees to come up with the next sub-goal for the robot, and then use model for planning and controlling the robot trajectory. So to that end, we actually propose a modular architecture that combine a learning-based perception module with a dynamics model-based planning and control module. So let me walk you through that module. So our perception module here is a convolutional neural network that takes as input the image that the robot sees, along with the goal position that it wants to go to, and it outputs the next sub-goal for the robot. Now, if you're not familiar with convolutional neural network, you can think of it as a parameterized function approximator that is particularly good at processing the images. Now, once we have the sub-goal that we want to go to next, we use the dynamics model of the robot. So this is the physics-based model to come up with a trajectory to that sub-goal, as well as a tracking controller to track that trajectory on the real robot. And then we get a new image and we repeat the entire procedure. Now, getting into a little bit more of implementation details here, the convolutional neural network that we use is ResNet 50 architecture. So this is a state-of-the-art image classification architecture in computer vision that we obviously have to modify and collect data on to get the sub-goal out of it. And I will discuss in a minute how to do that. But then once you have the sub-goal, we use a very simple 4-dimensional physics robot for the, physics model for the robot. So the model here consists of the X and Y position of the robot, as well as its speed and heading. And then we plan a trajectory using the spline-based planner, which is a polynomial-based trajectories that we plan over here. And then we use a linear feedback controller to track that trajectory. Now, obviously, the exact implementation details are not so important because this dynamics model and this planning module and this LQR controller, all these things would change as, for example, if I go from a mobile robot to a quad robot. But the basic idea remains same, which is to decompose the navigation problem into environment level reasoning via learning and system level reasoning via control. Now, here, the one thing to note is that our sub-goal consists of the next desired position that the robot should go to, along with a heading that the robot should approach this position with, sorry. And that is a specific design choice that we arrived at after several iterations. And it's a particularly important choice that I will comment more on in a few slides, but I just wanted to mention that for now. Okay, so before we talk about how we collect the data for this perception module over here, let's see this framework in action. So here on the right, you will see this magenta sub-goal. So that is being produced by the convolutional neural network based on the image that the robot sees on the left over here. And you can see the sub-goal here is guiding the robot away from the obstacle and towards the goal while maintaining a smooth trajectory at all times. So recall that this is in sharp contrast with the stop and go trajectory that I showed you at the beginning of when I started discussing this project. Okay. So obviously the elephant in the room is that we have a convolutional neural network sitting in our architecture. How do we get the training data for that? And the first thing that we tried to collect the training data for that convolutional neural network was reinforcement learning. And even though we got some success with that, but it did not work very well, especially when we execute this on a real robot. The next thing that people have looked into is kind of actually manually driving the robot around and to collect data on that. But those sort of approaches are just not scalable when you need thousands and thousands of data samples. Now, our key insight is that not only we can use learning and control together for navigation, we can actually use frameworks like optimal control to automatically generate the training data for these subgroups. And to do so, we actually train this framework entirely in simulation. In particular, we use this data called Stanford building data set. So these are the scanned meshes of 6 Stanford buildings. And what that means is that at any point in this building, you can ask what is the image that the robot would see. Also, you know all the obstacles because these are the scanned meshes. So we take one of these buildings and we randomly sample some start and goal position. And again, recall that just because we are in simulation, we know these gray obstacles. We won't make any assumption about the obstacles when we are testing this system. This is only during the training phase. And then we take this information and set up an optimal control problem. And the first step to do so is to define a cost function. In this case, this consists of two components. The first one is the goal cost, which is incentivizing the robot to go towards the goal. And the second is the collision cost, which is incentivizing the robot to stay away from the obstacles as much as it can. And then we ask ourselves, give me the robot trajectory that minimizes this cost function over the trajectory, such subject to system dynamics, physics of the system, the control bounds that the robot must address, and the current starting state of the robot. And there are several ways to solve these optimal control problems, which have been developed over decades in control community. But this is not quite the problem that we are interested in. This will give me the robot desired trajectory, but I'm actually interested in finding the optimal subgoal for the robot. So we modify this problem slightly, and we constrain the trajectories of the robot to polynomial trajectories. So now the robot can only follow polynomial trajectory in time, whose end point of that trajectory is the subgoal. And so we equivalently ask what is the right polynomial trajectory, or what is the right subgoal, such that that trajectory minimizes the cost function. Subject to obviously other constraints remain the same, which is the initial state and the control bounds. And so this process gives me the optimal subgoal for the robot at any position. Now, one thing I like about this framework is that even though here we only had two objectives, like reaching the goal and avoid the static obstacles, this framework itself is quite general. Later on, I will show you a video where we actually extended this work to now also navigate around humans. So we can very easily incorporate additional terms over here, and now the subgoal will be generated in a way which can actually anticipate and plan a trajectory around humans. Okay, so here we have is now a way to get image at any point, at any position in the environment, and the way to get the subgoal. So we keep collecting more and more data pairs like that. And once we have a whole lot of data samples, we train our convolutional neural network using supervised learning.
So I have a quick question.
Yeah, sure.
Why did you use the collision cost instead of a hard constraint on the position of the robot?
So that's a very good point, Shreyas. So actually, we can do that. The challenge to actually have a hard constraint is that optimal control can sometimes be too optimal. So meaning to satisfy, that constraint will be satisfied even if you just barely brush off the obstacle. Now, that was very challenging for neural network to reproduce that kind of behavior, because it will always have some errors. So we need to bake in some sort of error margin for the neural network. But other than that, you can certainly relax. You can provide some buffer around those obstacles and totally use a constraint instead of solving an optimal control problem. And in fact, I think there's a follow-up work that we have done with Mo where we actually do that.
Cool, thank you.
Okay, so far we have seen an architecture to navigate in completely new buildings based only on the RGB image, and then we saw how we can actually train such a convolutional neural network. But now let me go back to that stop and go video that I showed at the very beginning of this project and quantify some of those behaviors that we saw. Just to remind you, end-to-end learning essentially uses a convolutional neural network that takes as input the image that the robot sees, but now instead of producing the next subgoal for the robot, it directly produces the control commands to be applied on the robot. So that's the only difference. Now for fair comparison, we train this end-to-end learning module on the exact same data set that we train our own method on. And then we compare our method and end-to-end learning on a set of 500 navigational goals in an unseen building. So none of the method have seen that building before during the training phase. And you can see the proposed method performs significantly better than end-to-end learning. So we dive deeper into where this gap is coming from. And here I'm showing you some representative trajectories on from where that gap is coming. On the top row is our method, and on the bottom row is end-to-end learning. And here I'm only showing the top views for the illustration purposes. Remember that both methods are navigating only based on an RGB image. So what we saw is that end-to-end learning fails wherever we require very precise and nuanced control of the system. And that for this specific example means whenever the robot needs to go through narrow corridors or tight corners, those are the cases where end-to-end learning fails. And that's because it is ignoring the underlying physical structure of the system. So controlling in these kind of scenarios is particularly challenging. And when we looked at these plots, a natural question that we ask ourselves is that, oh, well, can we maybe overcome some of these issues with more data? So we then looked at the success rate of both of these approaches as we vary the number of training data samples for them. So again, here the x-axis is the number of training data samples, y-axis is the success rate along these 500 goals. Red is our method, gray is end-to-end learning. The numbers that I'm reporting on the top here are corresponding to 125,000 samples. But interestingly, interestingly, first of all, end-to-end learning method performance as well as our method performance is improving with more data, so that's not surprising. But the proposed method requires only 1/10 data compared to that of end-to-end learning to achieve the same success rate. And so that speaks a lot to the advantages of using the known physical structure in the learning loop for these systems. We also compared the jerk along the robot trajectories. And you can see the jerk produced by end-to-end learning is significantly higher than the proposed method, which is explaining that stop and go behavior that we were seeing earlier. And here is a representative control profile, which is being produced by the two methods. So again, red is the proposed method and gray is end-to-end learning. Now you can see there are sudden jumps in these end-to-end learning control profiles, and this has significant consequences for real robots. So for example, I was working at Skydio. Skydio is a company that makes drones for autonomous navigation. And there, if we will use profiles like these, the drone's life actually, battery life reduces from an hour to under 5 or 7 minutes. And to some extent, it is not surprising that the red profile here is smooth because we are using an underlying model for that. But we were actually surprised that these gray profiles are jerky because end-to-end learning was trained on the smooth control profiles that came out of that optimal control problem that we discussed a few slides earlier. But anyways, when we saw these jerky control profiles, we said like, oh, well, we can do a few things to smooth it out. For example, we can just maybe pass this profile through a low-pass filter. Or even better, we can explicitly penalize for this non-smooth behavior during the learning phase itself. And we tried both of them. And as a result, as you would expect, the profile, the velocity profile of end-to-end learning did get smoother. However, as a consequence, the success rate went down. So we saw this fundamental trade-off between performance of the method and the complexity of the control profiles it can produce with these pure learning approaches. And not only that, the proposed architecture is actually completely modular. We can actually take out this ground vehicle, turtle bot, and replace it with a quad rotor or even a walking robot. And we've been already working on some of these directions where some of the people I'm working with are actually using quad rotor, and we are actually actively chatting with Professor Kaushal Srinath here, who I think is also on the call here, who works on walking robots quite a lot, and something I really, really want to explore in future. Okay, so far we saw how this compositional approach that we are looking that we have developed for navigation compares with pure learning approaches. But everything so far has been in simulation. We train in simulation. We also compare them in simulation. But we were really motivated by real robot hardware experiments. So let's see what we can do on real robot. And the first thing that we tried was fairly crazy, which we said like, oh, well, let's take this framework which is entirely in simulation and let's deploy it directly in real world without any data collection in real world. And these experiments were all performed in Berkeley buildings, which if you recall, we trained the system on the Stanford building dataset. So obviously robot hasn't seen any of these buildings before. And here you will see 3 different views of the experiments. This robot view is what robot actually see to make decision. And then the top view and the third person view are only for the illustration purposes. So you can see, even though the robot has never been in this environment before, it can actually navigate around this very cluttered environment with bikes on one side and cubicles on the other side with a single RGB image. Moreover, the trajectory that the robot is taking in this case to the goal is very smooth. It's in sharp contrast with that end-to-end learning trajectory that I showed at the very beginning. So this is where this visual feedback that is coming through perception, but also the dynamics feedback that is coming through the physical model of the system is very important to get these kind of behaviors. In yet another experiment, so this is an experiment where we tested our framework in a very simple dynamic environment setting. So here, as the robot is moving towards the goal, my collaborator Varun here is actually moving the chair around to block the robot's path. But robot is actually able to react to this moving obstacle and plan a new path to its goal. Now, obviously, this is just a simple moving chair, but this was just really the first step at that point towards dynamic environments. Now we have actually extended this framework to navigate around real dynamic and to navigate around humans, so real dynamic environments, and I will show some results on that a little bit later in the talk. In this experiment, the robot starts inside a room and it needs to go to a goal which is outside the room. And here, the robot is actually able to learn that to exit the room, it needs to go through a door, even though it was never explicitly trained to do so. So these are the kind of navigation cues that we can get out of learning, which are very beneficial in new environments. But moreover, you see this glare on the floor towards the end. So when we tried a mapping-based approach for navigation in this kind of scenario, that completely fails here. And I showed some of these failure cases earlier, but this mapping-based pipeline fails around power strips on the floor, or thin chair legs, or when there is sunlight present in the room somehow coming through the window. And as a result, the success rate of mapping-based approach drops significantly in real robot experiments. And this is just really one example. As I said earlier, during the course of my PhD, I actually also did an internship with this company called Skydio. And they've recently moved from a mapping-based pipeline to a learning-based pipeline for navigation. And that's because this mapping-based pipeline was failing around thin tree branches like these, or thin electric power lines, or even when there are tiny water droplets on their camera lenses. And in all these scenarios, learning can provide a lot of robustness. In fact, in learning, we add a whole bunch of image distortions to our images, such as randomly changing their contrast, adding blur to them, changing their brightness, adding perspective distortions to them. And by adding all these distortions, we can make the system to learn to be robust to these kind of effects, such as glare on the floor. So let me take a step back and summarize what we have seen so far. So we started with the goal of unifying learning and control for operating in completely new environments. And we've seen one such framework to do so, where learning is used for the environment level reasoning and control theory is used for system level reasoning. And we have seen by division of these responsibilities between learning and control, we have been able to navigate the robot in a completely new environment based only on an RGB image. But this approach is not necessarily limited to navigation. In fact, we have some preliminary results where we combine learning and control for simple manipulation tasks or to navigate around humans. And here is, for example, a video or a snapshot of that work where we have extended that framework that we have discussed so far, but now also to anticipate and react to the human motion. Again, only on a single RGB image. So here we have created and used the data set to navigate around humans as well. Unfortunately, I won't be able to go into details of this work too much, but I just wanted to give you a preview of this work. But kind of for now, I want to shift gears towards some more imminent problems about these learning systems, which is that of safety. But before I do so, I wanted to just pause here for a second and ask if anybody has any question.
I have a question here.
Yeah, Mo.
So for the experiment with humans, where did you get the data for training?
So that's a very good question, Mo. So we actually have developed our own data set. So to the best of our knowledge, such a data set does not exist. So what we are using in that particular work is we are combining tools from computer graphics actually, along with optimal control to kind of create the data set to navigate humans in indoor environments, and then we use that data set to collect the training data.
Is it a photorealistic data set?
It's a photorealistic data set, yes. And we have released that data set, I think, as of last week.
Okay,
so
great.
it's available for everybody, and I'm happy to share
Okay, thank you.
more details on that. Yeah. Okay. So no matter how much you train these convolutional neural networks, they would still fail. So here is a snapshot of the same framework that we've been discussing so far in just now a new environment. And here, as the robot was going towards the goal, it collides into this chair. And that's because the chairs, if you recall, we trained this framework on the Stanford building data set, and the chairs at Stanford are apparently different than that at Berkeley. So it collides into them. Now, you will think about this that, okay, this is a slow moving robot, it's colliding into static furniture. That's not the biggest safety breach in the world. And it is not actually. But the same kind of issues happen for our autonomous cars, where these object recognition modules that are used in autonomous cars to detect humans and other objects on the road fails when there is a certain animal appears on the road. And that's because during training, a lot of these object recognition modules haven't seen many images with animals on the road. Now, the challenge with the learning modules is that it is very hard to pre-characterize all these failure cases. And so we need some alternative safety mechanisms to ensure system safety in these kind of scenarios. And the approach that we have been taking in our work is that of monitoring. So here, what we do is we monitor the output of the perception module and only provide a corrective safe action whenever necessary. What that means is that we let the learning module do whatever it likes to do, unless it takes an action or it produces sub-goal in our case, which might lead to collision with something, at which point we actually provide a corrective safe action to avoid that collision. So let's talk about how we can design such a monitor. So first of all, how to come up with a mechanism to figure out when we should interrupt, and then what is the safe action to apply in those scenarios. And to design such a monitor and safety framework, we need to make some assumptions. And the first assumption that we make is that the environment is static. It's still a priori unknown, so you don't know any of the obstacles in the environment, but it is static. The second, we assume that the robot has an occupancy sensor, which is perfect within its field of view. Now, obviously, it's an interesting question to ask what happens in dynamic environments or when the sensor is not perfect, which is true for pretty much any real-world sensor out there. And I will talk about how we can actually go past these assumptions. But for now, let's assume these are true and see what we can do with them. And so to understand our framework, let's consider a very simple example. So here, the robot is starting at this position and it wants to go to this green goal area. Again, it does not know this gray obstacle in the environment. And in this case, for illustration purposes, we are assuming the robot has a camera sensor on it. So it knows that everything within this light blue region is actually free. But it does not know anything else about the environment outside this light blue region so far. Now, in light of when nothing is known about the environment, we treat everything that the robot does not know about in the environment as an obstacle. So we assume everything in this gray area is an obstacle. Obviously, that's a very crazy idea, or seems like a crazy idea at least, because our goal now is an obstacle. But you will soon see that this allows us to provide safety guarantees in the environment, but also we will refine this gray area as the robot is moving in the environment. But given this gray area, we can compute something called backward reachable set. So that is the set of states within this red boundary over here. Now this set has a very unique and nice property that as long as the system starts inside this set, there exists a control to keep the system inside this set forever. So you start inside it, you remain within it forever. Moreover, within this red set, so okay, sorry, before that. So first of all, since we can guarantee that we will never leave this red boundary, that means we will never enter the gray region, and hence we can provide safety guarantees against unexplored and potentially unsafe part of the environment. But moreover, within this backward reachable set, so within this red boundary, we can apply any controller we like, including the learning-based controller that we have discussed in the first half of this talk. Only at this red boundary, we need to provide a safe action to push the system inside the backward reachable set. Now, in my work, I use Hamilton-Jacobi reachability analysis both to compute this backward reachable set as well as for the safe, to compute the safe action. And we will discuss how to do so in a few slides. But for now, suppose we can compute this set. Then, as I said earlier, we can apply any planner within this backward reachable set. Here, for illustration purposes, I'm using a sampling-based planner RRT, and consequently, the robot moves. So now the robot knows that everything within this light blue region is also free. And hence, it can update that gray region that we talked about earlier, as well as we can compute a new backward reachable set corresponding to that gray region. And we keep doing so until the robot reaches the goal. So let's see what this framework looks like. So suppose the robot started initially in an obstacle-free region, so that's that white region, and the red is the corresponding backward reachable set. Again, within this backward reachable set, any planner can be used. At any time, if the robot hits the red boundary, that's the only time safety controller intervenes and pushes the system inside the backward reachable set, at which point the learning controller can take over one more time. So this constant interaction between learning controller and safety controller happens until the robot reaches the goal in a safe fashion. Now, this is cool. So we can apply the safety, we can provide the safety guarantees in static environments, but to apply this framework, we need to compute and update these red boundaries in real time, which, by the way, none of which are like trivial tasks. So let me spend the next few minutes on discussing how we can compute these red boundaries, why it is challenging to compute them in real time, and how we can overcome that challenge. So as I mentioned earlier, we use Hamilton-Jacobi reachability analysis to do so. And to understand Hamilton-Jacobi reachability analysis, let's again consider a very simple example. Suppose we want to compute the set of states from which we can avoid this furniture or avoid collision in this furniture over here. Then the first step in Hamilton-Jacobi reachability analysis is to define a dynamics model of the system. And here we use a very simple 4-dimensional model that I showed earlier, except that now we add disturbances to capture any unmodal effects, such as friction between the ground and the floor, between the tires and the floor of the robot. Then the next step is to define the set of states that we want to avoid. So in this case, we don't want to bump into furniture, so obstacles are given by the furniture and everything else is free space. Let us see the same environment in a top view. So gray here is the obstacle and the white is the free space. Then, so one thing to note before I move ahead is that this is just an example. In the actual scenario that we're interested in, this gray region would be the all unexplored part of the environment. So everything that we haven't sensed yet, and white is everything else. But kind of coming back to this example, given this unsafe region, we define a function L of x, which is negative inside the obstacles and positive outside. And one such function for commonly known in robotics is sign distance function to the obstacles. So that could be one candidate for this L of x. And then we set up a zero-sum differential game between the disturbance and the control. So here, the control tries its best over time to push the system, to keep the system away from the obstacle as much as possible. And the disturbance tries its best to push the system inside the obstacle over time. And then we let the disturbance and control fight it out and figure out from which states the control would win and from which states the disturbance would win. And the solution to that set is given by the principle of dynamic programming, which in this case leads to what is called Hamilton-Jacobi Isaacs variational inequality. Now that's a mouthful, but if you're familiar with reinforcement learning literature, the Hamilton-Jacobi Isaacs equation is an equivalent of the Bellman equation for continuous time in presence of disturbances. So anyways, we can apply this dynamic programming, and this is what it looks like. So you start with L of x, so final value function, and then you apply dynamic programming, and value function ultimately converges. And once the value function converges, the sub-zero level set of that value function is what gives us our backward reachable set. As well as this computation gives us the safe controller to keep the system inside the backward reachable. So this is what this backward reachable set looks like from the top view now. So let's take the next few seconds to understand what is actually, what this backward reachable set represents. So recall that the value function here is a function of state, which is 4-dimensional. What I'm showing you over here is just a 2-dimensional slice of that 4-dimensional value function in the position space. Again, recall that the gray is obstacles, the furniture in this case, and we are looking at this slice for a heading of π/2, meaning the robot is facing upwards towards the top of the screen, moving with a positive speed. Now, when the robot started this position, this blue position over here, that means the robot has just barely enough time to stop and avoid a collision with the obstacle ahead. If we start with any position which is beyond this red boundary, that means the robot cannot avoid a collision with the obstacle. Hence, those states are as doomed as the obstacle itself for the robot. And that's what this retraction in the boundary represents over here. On the other hand, when the robot starts here, the robot has a lot of time to stop and avoid a collision with the obstacles, and hence the boundary of the backward reachable set is hugging the boundary of the obstacle. If I were to see the backward reachable set slice for a heading of -π/2, meaning if the robot is facing downwards towards the screen, you will see a retraction in the boundary here and the boundary hugging the obstacle over here. And these shapes are somewhat intuitive for this simple 4-dimensional system, but they get very complex as we move to, say, for example, quad rotors. But the reachability math itself is general and can be applied to general autonomous systems. Except the only challenge is that this is based on the principle of dynamic programming. So they suffer from curse of dimensionality. For example, to compute this backward reachable set over here, we require 52 seconds, which is simply not possible for real-time application that we're interested in. And so to overcome this challenge, we actually only locally update the safe set rather than updating it everywhere. Because at any given time, we only receive very small new information about the environment. And hence we don't really need to update the safe set everywhere. We can only update the safe set in and around the region where we are getting the new information. And so that's the idea of the local update. What I will do is, in the interest of time, I would skip some of the information, or rather move a little bit quickly through it, but just to kind of give you a very quick intuition about the local update. So suppose this light cyan region is where we have got the new information about the environment. So what we can do is we can update the local information, we can update the safe set only in this region and the region around it. So everything within this dark blue boundary is the place where we update the value function. Now, obviously, this is based on the principle of dynamic programming. So as you update the value function in this area, that affects the value of its neighbors, and then its neighbors, and then its neighbors. So you can see this blue boundary is growing in size, and we are updating the value function in more and more states. But at some point, this converges, and we get our updated value function. The nice thing about this computation is that we never touch this lower half of the state space. And that's where we are getting our computational savings from. In fact, first of all, we can prove that this somewhat intuitive idea leads to a guaranteed under-approximation of the safe set. Moreover, it reduces the computation time from 52 seconds to under 0.9 seconds. And I must mention that this is on MATLAB. We have another version of the level set toolbox where we can use tools like GPUs to parallelize the computation of backward reachable set, which reduces this computation time by a factor of 100 further. So now we have the ability to compute this backward reachable set in under 9 milliseconds. So let's go ahead and apply that now on a real system. So again, recall that this is the learning-based framework that I presented earlier, but now we have a safety monitor over here. And this safety monitor does nothing whenever the controller that's coming from this side is safe for the system. But whenever that tries to breach that red boundary, the safety monitor intervenes and overrides this controller by a safe control. So this is what it looked like in an experiment. So this is the same experiment where the robot was earlier colliding into this chair, but now you can see the robot is actually updating its safe set, this red boundary over here. And this time when the robot tries to move towards the chair, the safety controller realizes that that's an unsafe action. So it pushes the system inside the safe set again, at which point the learning takes over one more time. And one more time, you will see the learning is actually trying to take the system towards the obstacle. The safety controller will intervene one more time again and pushes the system inside the safe region. So through this interaction, the robot reaches the goal, but in a safe fashion. But more importantly, what this red set over here represents is that area of safe exploration in which learning can be performed without worrying about violating the safety guarantees of the system.
Somil, in this case, does the robot know its position exactly?
Yes. So throughout all these works, I'm assuming perfect localization. That's a very good question, Sanjay.
All right, thank you.
Yeah, no worries. So let me summarize quickly what we have discussed so far. So we started today's talk with the aim of developing mathematical tools and algorithms for learning and control for robotic systems. And first, we discuss a framework that uses learning for the environment level reasoning and control for the system level reasoning to operate the system in completely new environments based only on the onboard sensor. We then talked about that we don't have to stop at that point. We can actually use this model to monitor these perception modules.
I'm sorry, Somil. So sorry to interrupt. Could you mute whoever SK is? I can't hear you.
SK is not responding to my chats. Yeah. Okay.
Thank you.
Yeah. Let me
Go ahead.
SK. Okay. Yeah. Sorry. And the second thing I was saying is that we don't have to just stop at that. We can actually use models to also monitor the failure in the perception module and provide a corrective safe action wherever necessary. So in this way, by combining learning and control together, we are obviously operating in new environments, but doing so in a data efficient and safe fashion. Now, at this point in my talk, I'm realizing I'm like at 5 p.m. and I would love to discuss some future work, but in the interest of time, what I want to do is maybe discuss the future work some other time or in some other opportunity, and spend the next few minutes to thank people who have been instrumental in actually this PhD journey of mine. Now, this PhD by no means will be an achievement of will not just be my achievement, but rather that of a set of phenomenal people that I'm very lucky to have in my life. First, I'm thankful to these amazing professors whose office doors have always been open to me whenever I wanted to discuss about formal methods or machine learning or computer vision or just control barrier functions, or when I just needed advice on research or mentorship or how to do networking in conferences. So thank you so much for your amazing mentorship over the past 5 years. Next, I want to thank my advisor, Professor Claire Tomlin. And unfortunately, I don't have many candid pictures of Claire. I found one, this from her birthday celebration. And oh my God, I can write pages and pages to describe how lucky I am to have Claire as my advisor. It is really people like Claire who give me courage and excitement to pursue a career in academia. She's the one who really kept me going through highs and lows of my PhD. She always had my back whenever I was venturing into deep learning and could not get any result out for 1.5 years, or when I'm trying to set up a crazy flight test bed without any success for 1 year. And one thing that I noticed over the 5 years is that every week, Mondays 9 to 9:30 a.m. has been the most happiest time of my weeks over the past 5 years. And that's because that's the time when I meet, I have my weekly one-on-one meetings with Claire. no matter how stressed I am going into those meetings, but I will always come out of those meetings smiling and being happy. I will always come out of those meetings knowing more about myself, believing more in myself. And so thank you so much for all that mentorship, Claire. And Claire is not just a great mentor, she's a great teacher. And above all, she's a wonderful, wonderful human being. So thank you, Claire. This wouldn't have been possible without you by any means. Next, I would like to thank some staff members without whom my PhD life would certainly would have been very difficult. So I'm very lucky to know these three people, and Sylvia and I often talk about them as three angels, Shirley, Angie, and Jessica, who have helped us from so many things, from like filing reimbursement to managing our recommendation letters or to answering over 1 million questions about the department. So thank you for your support. It has been really instrumental in my PhD. I'm very thankful to obviously all my amazing collaborators without whom this work wouldn't have been even possible. Special shout outs to Alexandra and Roberto for guiding me through this domain of learning. Thank you for your mentorship. I'm particularly, I would say, fortunate to know these two amazing people, Mo Chen and Sylvia Herbert. They've been like really really the part of, I would say, the golden days of my PhD. I have learned so much from them. We will brainstorm together, we will work together, we'll eat together, attend conferences together, organize tutorials together. It was just a phenomenal, amazing time, both from a personal and professional standpoint. So thank you so much, guys. Second, I would like to mention these three people whom I've learned a lot from about robotics, Andrea, Varun, and Alice. Now, not only have I learned so much about robotics from them, but also these three people have this amazing ability to juggle between theory and robots, and I still don't understand how they can juggle between them so seamlessly. And really all the videos that you have seen in today's talk, I was not actually there in the room when those videos were filmed. And that's because whenever I'm in the room, somehow my robots refuse to work. They would always collide into the obstacle or the humans, essentially anything that you don't want them to happen exactly happen when I'm in the room. And so these three people somehow have their way with the robots, and that's why I also like to call them the robot whisperers. So thank you so much for all the amazing collaboration and memories that we have throughout the past 5 years. Now, other than a bunch of papers, the one thing that I've got out of my PhD is this set of amazing friends. They have been really there for me whenever I'm in this philosophical mood that's coming out of the existential crisis in PhD, or whenever I'm just nervous about a presentation, or networking in conferences, or just faculty applications, or when I just simply need to rant over a drink. These people have always been there for me. And not just these people, the entire hybrid systems lab and the semi-autonomous group has made me feel Berkeley like a home. So thank you so much. And I'm lucky to have shared my PhD life with all of you. A special shout out to all our Indian gang. I mean, I'm pretty sure they won't like this word later on, so I'm gonna get a lot of messages about that. But these are really the people who have been my second family over here in US, away from home. I cannot even imagine my life in US without these people. They have been by my side in my worst and in my best over the past 8 years. And like helped me with so many tough decisions in my life. But I think those are the tough decisions in my life. Or when I simply need to eat some good home cooked Indian food, they have been there. But really, really, thank you so much, guys. It wouldn't have been possible without you. And obviously, this journey wouldn't have even started without my family. I'm particularly coming from a background in India where education is rather an exception than a norm. So without my family's constant encouragement and support, I wouldn't even have dreamed of pursuing a PhD. So I dedicate my PhD to this amazing family of mine, which I can only be lucky to have. Sorry for going over time, but thank you so much again, and I'm happy to take any other questions.
Thank you, Somil. I think we're all clapping, either virtually or you can see the people clapping. And now it's time for some questions. So please feel free to unmute yourself and ask questions.
Well, maybe I'll ask a question just to continue the tradition.
Yeah.
Go
ahead, Mo.
So, so for the work on sensing at the environment and then recomputing reachable sets, why is it necessary to compute the infinite horizon reachable set when you're going to update the reachable set right away?
Good question. You don't have to. In fact, I hinted that we proved the guaranteed under approximation of the safe set, and that under approximation is guaranteed at each time step throughout that iteration of value function. And in our real robot experiment, we actually do not compute the infinite horizon set. We compute a smaller horizon set. It just have to be greater than your planning horizon.
Okay, thank you. Congratulations.